and another pole is going to be here, okay, somewhere here, this cross sign P2. Okay, so since, okay, for this causal, okay, causal system, one pole is outside of the unit circle, the system is, okay, the system is outside of the unit system is unstable, okay, unstable. So to summarize what you have learned so far, that if I give you the difference equation, what you need to do, you need to find the h of z, right? And this is causal system is already mentioned, and you can see from this difference equation, you need to find the poles of the system. You try to see if the pole is outside of a circle. I have drawn two poles for this particular system. I see one is sitting at outside of the circle. This is 2, this is 0.5, right, 0.5. So that's why for this causal system, one pole is outside of the unit circle. That means the system is unstable. Okay, good. So that's it for this case. Now the last thing we are going to learn, the relation between Z transform and the discrete time Fourier transform. Okay, so this is the slide. We already know how to calculate discrete time Fourier transform, right, in handout number 3. Okay, we know how to calculate the discrete time Fourier transform of a signal, right, or impulse response of a system, right, in handout 3. Now we are going to see if there is a relation between Z transform and the discrete time Fourier transform. In fact, one student asked me a couple of class back that Dr. Hossain, Z is a complex variable. We can take any value of Z we want, right? Of course, we should this xz has region of convergence, means there are some good values of z that defines the region of convergence to have this capital xz or z transform of a signal or discrete time system will be convergent, right? We know that. However, within region of convergence there are many values of z, good values of z, right? Which one should we pick up? It depends, right? If we talk about discrete time Fourier transform, you will see that we should pick up certain values of z from the region of convergence, right? So if we put z is equal to, in this case, I'm sorry, I have expressed in terms of frequency, right? But I usually will do in terms of omega, okay? So if we have z is equal to j omega, right? So this is, if we plug in z is equal to exponent j omega, what we get like this, right? Okay, omega, this is j omega, okay, j omega, exponent j omega, we get here, if you look carefully, okay, so this is going to be j omega n minus j omega n. So does it look familiar? So this is actually discrete time Fourier transform of the signal xn, right? So this is gonna be the I have a different notation here, I'm sorry. So it should be, this is familiar, right? So this is basically your discrete time Fourier transform of the signal xn. So bottom line, we can find a discrete time Fourier transform signal if we know its Z transform. What we need to do, we need to go to the Z transform expression and we plug in Z is equal to exponential j omega, right? And we get the discrete time Fourier transform of the signal. So now you see that we are using a particular value of z, right? and that gives me the discrete time Fourier transform. So that's the important point here. Okay, so that's what we need to do. Okay, good. So this is the relation. So now let's look at one example. Recall handout number 3. Okay, handout number, let me go to that handout. Handout number 3. Okay, handout number 3. I'm going to tell you recall. Okay, recall example. Okay, handout 3, page number 23. Okay, 23. So xn was given. Okay, given. Okay, that means xn was a to the power n un. Okay, and a was, let's say, 1 over 2. And we know discrete time Fourier transform. Okay, discrete time Fourier transform of xn, right, was, if you look at that example, was, was 1 over 1 minus, okay, half times exponent minus j omega. This was the case, right? So that was the case. Now can we find same thing from Z transform? So okay, so now to find, okay, find we say x omega, right? Okay, now to find x omega from xz. Okay, so for xn nun, okay, xz, right, xz is 1, we know that 1 over 1 minus a, actually 1 over 2 z to the power minus half, right? This is the case, and we have a region of convergence outside of a circle. We know that 1 over 2. Okay, so how do we find x omega? X omega is going to be xz, right, evaluated at z is equal to exponent j omega, right? So that's what we are gonna do. It's going to be 1 over half, right, exponent j omega. Okay, so we got the same answer, right? So these are same as what we have learned during handout number 3. Okay, good. So what we are learning, if we know the Z transform of a signal, we can find the discrete time Fourier transform. If we plug in a particular value of Z, that Z is exponential j omega, and we have solved one example. Okay, good. Similarly, if we know, okay, so note, one side note, if we know, okay, ace of n, okay, if we know ace of n, if we know ace of n, we can get ace of z, right? So ace of z, which is z transform of the impulse response. If I know impulse response, okay, we can calculate ace of z, okay, we can get az. Also we can get, this is called system function or transfer function in z domain. We can get ace omega, okay, which is ace of z, right, evaluated at z is equal to exponential j omega. Do you know the name of this thing? This thing is called, okay, this ace omega is called, okay, system's response, okay, system's response, okay, system response in frequency domain. Okay, this is called system frequency responses. Okay, this is complex in general. Okay, this is complex in general, and this is called H omega is called systems response in frequency domain or systems frequency response. I'll talk about the significance of that bit in the next handout, okay? But the whole point here, if I know the impulse response of a system, we can get capital H of Z by taking the Z transform of the impulse response, and we can also get H omega by evaluating H of Z at a certain value of Z. Z is equal to exponential J omega, and this H of omega is called systems frequency response or system response in frequency domain, and this is complex in general. And we know that when you have a complex things, we have both magnitude and phase. We'll talk about that in handout 8. Okay, good. So that's all for handout 7, and we'll continue for handout 8 in my next video.